Hello, class. Here we have a guest student with us today, Jen Bones, as we discuss the principles of circular motion and go over the concepts in our lab number 6, which deals with circular motion and mechanical energy. So Jen Bones over here is playing with some of our circular motion demos and the experimenting with the idea of inertia. And that is, once an object is in motion, it continues with that state of motion unless a net force changes that. So circular motion is a big demonstration of how inertia works, because in order to make an object undergo circular motion, we have to force it to go in a circular path. So if we take Euler's disk here, in order for me to make it go circular or undergo circular motion, I give it a force, I apply a net force on it, and it spins. Okay, so any other top two will spin. So if I take a force, I can make this object spin. And if there were no air resistance slowly slowing its motion, it would continue spinning indefinitely from that applied force. And the same goes with any other top here. Okay, we obviously have an imbalance of mass here, but once an object starts spinning, it will continue spinning indefinitely from that applied force. But we need a net force to make it go around the circle. And this.
All right, given the constraints of how fast an object can be going at the bottom in order to just make it over the top, I'm going to attempt to do this with water. See, there is actually water in here. Water in a bucket. Okay, and so I'm going to swing this over my head, but I better give it the square root of 5rg velocity at the bottom, so it'll have the square root of rg velocity at the top.
Dr. E had the magic swing.
That was close. Okay, let's see if it happens. What happens if it's a little less than that? Whoa!
Oh, no.
Okay, so see, really, you do need to give it that velocity, or else the water could fall out.
Did it fall?
A little bit came out, not that much came out.
Oh, that time, no, that was good. Yeah, only when he went really slow, the whole bucket.
Yeah, when I
came.
went really slow.
Then it fell out. Yeah, then it came out.
So Dr. E and the water in the bucket.
See, a little bit dripped out there.
Experiment. There you go. Nice. And Mark is going to try the water in the bucket experiment and trust his physics. Slower.
Oh! Gotta go faster than that. There we go.
Where'd the water go? Nice. Now, why does the water in the bucket not fall out? Let's take a look. Is there really water in there? Mr. Jet, our physics assistant for today? Yeah, it's got water, and he is not getting any water. Show us a good demo here. Contestant number 2, Dane. Now, he's able to spin the bucket of water fast enough so the water does not spill out. In this case, instead of the water in the bucket, we're going to have the ball in the bucket experiment with our Dr. Seth, our famous physics assistant. So can you spin the bucket fast enough so the ball does not fall out?
Yeah, probably.
Let's see you do it.
Good?
Wow, look at that. Go, Seth. Looks like you're giving it enough centripetal force so that it doesn't fall out. Now go slower. Slow. Does the ball fall? Can you hold the bucket vertically over your head? Ah, we lost the ball.
No, I didn't.
Okay, hold the bucket over your head vertically.
Watch out, watch out, watch out, watch out.
That's what it does under normal circumstances. Hello, physics students. I'm here with you today to go over some circular motion concepts and problem solving that we will see and work with in this lab number 6 here at Cuesta College for our physics class. So as usual, and as we've seen with our previous labs, we'll have 2 main parts. Our first part will deal with simulations based on circular motion concepts, looking at a variety of circular motion problems and simulations, and collecting data and doing calculations and then answering questions based on those. I'll also have just a little bit of energy simulations included with those. And part 2 is do-it-yourself experimentation at home. We'll be looking at doing circular motion, making a conical pendulum at home. And we'll see what a conical pendulum is. Here's one example. There's many others that I will show you. And looking at how to time the periods of rotation of a conical pendulum and measuring the angle and seeing if we could figure out the velocity of this conical pendulum. We'll look at simple pendulum and conservation of energy, and we'll recreate the ramp we did in the last lab and look at conservation of energy and apply our work energy principles. All right, I love circular motion. Spinning things are very interesting. So we have a lot of amusement park rides that come into play when we look at circular motion. When we look at the cosmos, everything is rotating out in the cosmos. We have moons going around their host planets. We have satellites, artificial satellites that we put into orbit around planets that are going around in circular motion. We know that Earth goes around the sun 365.25 days in one full orbit. And of course, the entire solar system is orbiting the center of our galaxy, and that takes like almost 240 million years. So everything is spinning in the cosmos. So what we have to understand and get to at the heart of this lab when we're looking at all these examples and in problem solving in general for circular motion is what is creating this circular motion. So we have to understand Newton's laws here and the principles behind it and how we apply it to understanding the mechanism behind the circular motion. So in any case of circular motion, you have a net force. It takes a net force to make an object go in a circle. Otherwise, it's going to want to go in a straight line path. So here I have a ball on the end of a string, very typical example for circular motion. And if I could keep it uniform, meaning at constant speed, I could get it to spin at a constant speed. But this ball has acceleration. It's called centripetal acceleration, a center-seeking acceleration, because it's changing direction, okay? And that acceleration is proportional to the net force. I'm applying a force on the ball. I'm applying tension on the ball, and I'm forcing that ball to undergo circular motion. And that force points towards the center of the circle of that path, and that is the centripetal force, which is proportional to the centripetal acceleration, which is proportional via the mass. Now, another word for centripetal force is the radial force, or another word for centripetal acceleration is the radial acceleration. So sometimes we use 2 different notations. So very important idea. It takes a net force to make objects undergo circular motion, which is called the centripetal, some people call it centripetal force. And I'll do 2 notations here. We could say FC. A lot of older textbooks use the FC notation, or FR. Okay, so, whoops, we need our L in centripetal. So we need that net force. So behind any circular motion, there's either one force or a combination of forces that make it go circular. So that's centripetal or radial force, which is proportional to the centripetal acceleration it experiences. And we have the notation AC, or the radial acceleration, which points towards the center of the circle. This is important when we're doing the problem solving, especially when we're looking at these different simulations. When we're doing our free body diagrams and our equations of motion, we're going to have a radial direction. So before I get to that, there's two main things that you want to be aware of. So you have to note there's two types of circular motion. We want to break down every problem into the category of being uniform circular motion or non-uniform. Okay, so we're going to concentrate on the uniform because the non-uniform can get quite difficult. So note, there's two types of circular motion. So hopefully this is a review to you. There is the uniform versus non-uniform. And in our simulations, we're going to have 5 of these simulations. And when we begin with the conical pendulum, that is an example of uniform acceleration. So let me go over what the difference is. So in uniform acceleration, you only have centripetal acceleration only. In non-uniform, you have centripetal acceleration and a tangential acceleration. And remember, these are vectors, even if I forget my little hats here, okay? So what this means is uniform circular motion is when it's going around in a circle at a constant speed. You still have acceleration based on the change of direction, okay? So anything that you spin and is going around at constant speed, like you're playing a record at 70 RPM, it's going around at a constant speed, it has a center-seeking acceleration. Non-uniform has that center-seeking acceleration, but also is changing speed. So you could speed up as you're going around a circle. Like maybe a car is driving, it's going 20 miles per hour, 25 miles per hour, 30 miles per hour as it's going around a circular path. So that's an example of non-uniform. So this is constant speed, changing direction, and this is changing speed and direction. And you could show this vectorially. So circular motion, some of the most important ideas when you're problem solving with circular motion and approaching the problems to this lab is you want to always identify the center of the circle, the center path. Okay, you're always going to have a radius, which is the distance from the center to the side, any part of the arc of the circle, I should say. The radius. Okay. And if you're an object undergoing circular motion and you're going constant speed, you reflect that by having the same size vector. So if each one of these are your speeds, v1, v2, v3, then your delta v would always be your centripetal acceleration. Okay, what's going to happen is when you take the difference of those vectors, if I say v3 minus v2, v3 minus v2 would point towards the center of the circle, as we see. However, if you start changing speed on this side, let's say we go here, we're going to increase our vectors, you're going to see that not only do the lengths change, but also you're going to have both the centripetal AC and then you're going to have a tangential acceleration this way, and AC, your tangential and your centripetal acceleration are related via your total acceleration will be the square root of ac squared plus at squared. And I have that in my little summary of formula. There's a lot of circular motion relations that you want to go back and forth with. Now, important idea when you're thinking about rotating circular motion, all objects, like if they're on a disk, are all moving with the same angular speed, angular velocity. And we have a different way of representing angular velocity versus tangential velocity, the v that we're used to. Okay, so I'll go over that shortly here so that we'll have that background for our lab ideas that we're going to look at. Okay, so first identify whether it's constant speed circular motion or not. Okay, very important. Tangential, when you have tangential, you have to get your total acceleration that way. The next bits that we want to be aware of is being able to relate our variables in a rotating frame of reference, things that are rotating, to a translational frame of reference. So far we've been doing all the translational mechanics, which means that, or linear velocities, which means that all points move with the same velocity. However, if you're spinning, not all points move with that same velocity. So what you have to be able to, so some more important notes here, is be able to relate translational, say linear variables, back and forth to rotational variables. Okay? And your textbook or many websites go over this idea is if you're viewing objects rotating, you need to have some way of communicating how everything's rotating, the motion of all those objects in that rotating frame. Now, if you're on that rotating frame, you know, you're measuring things like we're on a rotating Earth, but we could do translational velocities. We can measure V. We know that all points move at the same speed. You know, we don't have to take that rotating part into consideration. But if we're viewing rotating frames, we need to have some way of translating it, right? So it's like if we have wheels on a bicycle tire, we need to be able to relate how much distance our tires transverse on the ground versus how fast they spin. So very important ideas. So what we have is for translational variables, we've been dealing with velocity. And we want to relate it to our angular velocity. So this is our linear velocity. We're going to use this a lot, linear velocity. And here is our angular velocity, omega. And our standard units are meters per second, where this is radians per second. Okay? And the difference, so if you're on a big disc, you know, like a rotating merry-go-round, I'm going to bring a bicycle wheel here. Because of course, we have good examples of rotating frames. So here we have a bicycle wheel. So all the points on the wheel rotate with the same radians per second, the same omega. However, if I'm right here, my meters per second will be different than my meters per second at this position, which will be different than my meters per second at this position. So my velocity, my V value, will depend upon how far from the center of the circle I am. Okay, so if we look at a wheel, or any problem in general, all the problems that we're going to do in this lab, here's your radius value. Your velocity here, V1 will not equal what V2 is. Okay. What's going to happen is V2 will be greater than V1. Now, what about omega? Omega 1 at this point. And let's say this is omega 2. What we do know is that the angular speed will be the same at each position, anywhere along there. Okay? So your radians per second value will be the same throughout. And you got what you want to think of as too is if this is a rotating disk, let's say it's rotating in this direction, which would be counterclockwise. We'll get more into those facts a little later. So if we're rotating this way, all points are forced to move that way. And what happens is they're all feeling the laws of inertia. They all want to go in a straight line path, but they're being forced to go in this circular path. So you can see how the effects of inertia will increase the further out you go. So you're going to feel those effects. So they want to go out in a straight line path. And at some point, depending upon how the materials hold together, like if you took pizza dough and you're rotating it, all those pieces would fling outward if you're spinning it fast enough. Then you get into tensile strength. Okay, so really important idea. So this is a very important formula to use. And some other relationships we have that come up in this lab are how we relate our angular velocity to the period of rotation and the frequency of oscillation. So omega is equal to 2 pi times the frequency of oscillation. And remember, this is measured in hertz. 1 hertz is equal to the reciprocal of a second. That's how many cycles per second that it undergoes. So, you know, if you're going around like 5 times in a second, you get something to spin 5 times per second, that would be the number of hertz it is. Okay? And this is also equal to, instead of frequency and the period of oscillation are reciprocals. So this is frequency. This is the same thing as 2 pi over the period of oscillation, which is how long it takes to complete a cycle. And we typically have this, when we're working with this other units, we want to convert this to seconds. So we could talk about the period of oscillation, the period of the Earth going around the sun. That's 365.25 days, but we'd want to convert that to seconds. Okay? Or if we have a satellite that's in geosynchronous orbit, what that means is we want the period of that satellite to match the rotation of the Earth, about 24 hours. So that's always in a fixed or relatively fixed, which is difficult to achieve, a position above the Earth. So if you're at a certain city on the Earth and you're viewing the satellite, you're always going to be able to view this satellite because you're both rotating at the same 24-hour period. Okay. So what happens is we would have to convert that 24 hours to seconds. So this is a very important relationship which you could substitute into your formulas here. Okay. Now a little later on you're going to get to 3 quantities, like angular quantities are a little different than your linear quantities. So instead of displacement, like you'd have delta x, we would use delta theta for displacement. Delta x, delta y, or delta z. Instead of v for velocity, we would use omega, or angular speed. And instead of acceleration, straight out acceleration, we would use alpha, angular acceleration. Okay, so we'll get to those details, but these are the main ones that you need to use. So let's take a look at
In this lab, we're going to be exploring the conical pendulum with a couple of different techniques. One, we're going to actually set up a conical pendulum. And in the second, you'll have a computer simulation in which you'll be working with what looks very much like a conical pendulum, where you can adjust the values of R and the mass and that sort of thing. And so the idea then with the conical pendulum is that we are rotating an object around with a certain angle theta with respect to the vertical. And we want to try to maintain a constant speed as we get this mass to go round and round in a circle. And so we can measure the R. Now the R value is not this value, but rather the distance from the mass to the center of spin. That's this value here, because that is the horizontal circle that the mass is moving through. And so there's only a particular velocity that will balance out the centripetal force and the gravity forces so that they'll be in equilibrium for a particular value of theta. And so we can measure the R. We know this distance here. And if you have a meter stick, you could just project down onto the surface and see where your ball or whatever the object is that you have connected to the string crosses the meter stick, and then that would be the diameter of your circular path, and then you could make a rough estimate of the radius itself. Once you have that, then we can write the equations that are relevant, and also recommend that you look at my section on the conical pendulum in my lectures as well. So here we have mg acting down. The tension force at any given moment is going to act up like this. The angle theta we can measure from the vertical, and so that means by opposite interior angles that that's also the same thing as this angle measured with respect to the tension vector. So that we have t cosine theta balancing out mg, t cosine theta minus mg equals 0, or t cosine theta equals mg, and then the component that acts toward the center of spin, where this radius here is r, this is going to be t sine theta. You have t sine theta equals mv squared over r. Okay, so those are our two equations and two unknowns. The unknowns are the velocity and the tension in the string. And so we can write this then in a form that doesn't have the tension in it by dividing both equations through, giving us the tan of theta equals v squared over rg. And once we have that, we can solve this for the velocity. That's equal to the square root of rg tan theta. Okay, so in your simulation, r will be given to you, but here you can measure the r with that technique that I suggested before, with you superimposing, looking down from above on a meter stick as the conical pendulum moves along. Now you can also measure the period of this orbit, and so that period shall write out as the period rather than writing it as a t, is equal to 2 pi r over v. Okay, and so that period then can be gotten from this expression for the velocity by just saying that rate times time equals distance, and the distance that you travel in one complete cycle is equal to the circumference of a circle that has a radius that's equal to r. Okay, and so the period then can be measured and then can be compared to the value that you get by plugging in for the velocity square root of rg tangent theta, and then you get your theta by knowing what r is and by knowing what the length of the string is. And you can say that the sine of theta is r over the length of the string, and then that would give you theta, which you can use for that part of the expression. Now if we want a relationship between the period and the radius, we can say that by plugging the velocity into the this expression for the period, we get the period is equal to 2 pi r divided by root rg tan theta. Then if we square the period, square both sides of this equation, we get the period squared is equal to 4 pi squared over g tangent theta times r. And so in one part of the lab, you'll be asked to plot the square of the period versus the radius for the simulated conical pendulum, the computer simulation for that.
Okay, for a conical pendulum, basically what we have is any mass on the end of a string. And what we do is we get that mass to undergo uniform circular motion, so constant speed along a circular path. So what we're going to have is we're going to have a defined radius value, r. So we'll have a radial value, and we'll have an angle, theta, and we have our string, which has a length, L. Okay, so this is our mass right here. And we could create this with any sort of string and mass tied on the end. So here I have a homemade do-it-yourself conical pendulum, which is what you're going to do. And you could trace out a circular path underneath, measure the angle with respect to the vertical, and you get this, you keep a steady tension, and you get this to be a consistent, constant speed as it goes around, okay? And you want to look at the effects of the tension, the angle changes, the radius path, and see how all those affect one another. And to do that, you want to look at your equations of motion. Here's a hexagonal nut. This also can make a conical pendulum. You could rotate that at a nice constant speed as well. You get really big, right? You can make a giant conical pendulum and sweep out a radial path and see how the length changes affect the circular motion and all the other variables, okay? And also think about how the mass on the end of the string works in the equation, whether you need it or not, to solve for certain variables. Okay, so my components will be FTY will equal, when you take a look at this, FTY will be cosine, will be FT cosine theta, and then we'll have FT radial, the radial component of tension, will be FT sine theta, as you can see right over here. Okay, it's the opposite. Either way. So very important. Now our equations of motion, which will give us everything we need to approach the problem solving and the questions, will be the sum of all my y forces equals mass times acceleration in the y direction. There's no acceleration when you look at a conical pendulum. There's no up-down acceleration. There shouldn't be anyways. It should be all along a radial path. That should be 0. And what makes that up is the y component. So the y component minus Fg equals 0. The weight force, or in other words, we could say, since we have our components here, Ft cosine theta minus mg equals 0, or I'm going to go ahead and just say equal to 0. Equal to mg, since it equals 0. And that gives me one of my equations of motion. Okay, I don't know my tension, but if I know my angle, my mass, and my g, I can figure out what the tension is. Now my next equation will be the sum of all my radial forces or centripetal forces. Sometimes you'll see an R, sometimes you'll see a C, so I'll use those interchangeably, equals mass times radial or centripetal acceleration. And the centripetal acceleration is the v squared over r acceleration. Now what makes that force up, what makes it undergo circular motion, is the radial tension component. So here we have FTR will equal mv squared over r. I'm going to make the substitution. Centripetal force is equal to v squared over r. And I probably should have had that up earlier, but if you do your substitutions, you'll see that that goes. Okay, so we have our mv squared over r, and the next thing we have here is we do our substitutions and we get ft sine theta equals mv squared over r. And that gives you another equation. Now let's say you wanted to solve for v. How can you get v in terms of all the other variables? Well, let's see if we could substitute this ft into that ft. If I sub 1 into 2. And I'm going to do this to see if I can make some simpler relations and use less quantities, because if I don't have a mass, like I don't have the mass in the simulation, I don't have velocity, all I have is the radius, I don't have the angle, and I don't have the actual value of the tension force. So let's go ahead and see how many we could eliminate. So if I sub 1 to 2, this ft is equal to mg over cosine theta. So if I sub that in here, I'm going to get mg sine theta over cosine theta equals mv squared over r. And here you can see how nicely your masses cancel. And you get tan theta times g equals v squared over r. And that will allow you a lot more flexibility. So now you don't need the mass, and you have angle, velocity, and radius equations, relations you can work with. Now, furthermore, velocity, okay? How can we help find that using anything else we know? So in this simulation, we're also looking at the period of oscillation. So what we're doing is we're going to see how many times we're going to time this. We do have timing here. So we're going to look at 4 cycles will equal so many seconds in time. And then we can find the period of oscillation, t, our period, will equal the time divided by 4, and we'll get so many seconds, okay? And by timing this, finding the time here, that will give us some information to help us find our v value. So here, what we do note is that v, if you recall, is equal to r times omega. Okay, this is how we relate linear velocity to angular velocity. V equals r 2 pi over t. And so if we have a period of oscillation, and an r value, so you have this, and you have a period of oscillation, you'll get v equals so many meters per second. Once you have that, you could plug that in. You could solve for your angle, because you know what little g is. The other thing to contemplate is how that g affects, the little g, the acceleration due to gravity, will affect this oscillation as well. So, you know, if you're on Mars and this is 1/3 of the value, you could see how it would change your velocity values. Okay, as well. So this is that's the start on doing all the other questions here. But this is really the core of doing the conical pendulum, doing substitutions with your equations of motion and getting it set up correctly. The next simulation is one that changes what your centripetal force is. And that's like having an object on a rotating disc. And you could use the analogy of, like, you know, a person on the merry-go-round. How fast can you spin it before you make them fly off? So if you have a spinning disc, maybe you have a record player and you put a penny on it, how fast can you spin it to get it to slip? And what variables can you solve for in the process? So the second simulation, so here we have a uniform circular motion demo. If we spin this record at 33 RPM and we place a penny at a distance r from the center of rotation, will it stay on there? So what we have here is we'll have the frictional force between the penny and the record enough so that the penny will undergo circular motion with the record at 33 RPM revolutions per minute. Let's see how this goes. Okay, as you can see, it is not slipping. Okay, so now what we could do is increase the radial distance, and what will happen is it'll spin with the same angular velocity. However, the linear velocity will increase by the amount of increase for the radius. Okay, let's go ahead and take this for a spin. Okay, so 33 RPM is not enough to make it slip, so it's still held on by the static friction force. Now, if I turn this off and I change my spin speed, my angular velocity, to 45 RPM, let's see how this works. A faster spin will result in the penny slipping or not? Not yet. Okay, so here the static friction force is still enough to hold it on and force it to undergo circular motion. So the static friction force is the centripetal force that points towards the center of this spinning disc, this circle. If I increase it to 78 RPM, what will happen at this radius? So let's increase the spin speed. Whoa, and there it goes. The static friction turned into kinetic friction and slipped off. Just a quick setup here. The second simulation is just a disc on a turntable or an object. I'm going to say mass. So a disc on a turntable here. And what we have is we have a defined radius. So we have a center of a circle. We have a defined radius. And if we put this other disc, maybe a coin, here's a record, here's a coin, or here's a coin on a turntable, and we're going to get to spin. It's going to spin round and round. Okay. So it's going to have some sort of mega. The question is if we have this spinning, what is the force, that's the centripetal force that's making this disc, this mass right here, this is our mass, undergo the circular motion? And at what point, if any, will this fly off? And also, what's the velocity of this mass? What's the centripetal acceleration? Can we get all that information from that? So if we have a mass on a disc like this, it's important to identify all the forces. So here, again, our free body diagram will give us some information. So I have this mass and it's rotating. And so I'm going to define my radial axis this way, my y-axis this way. And then if I look at all the forces on my mass, I'm going to say, well, what I have here is this disc is sticking onto this turntable. So it's a sticking force, so that will be static friction up to the point it slips where it's no longer. So I'm going to define this free body diagram at the point it slips. So I'm going to define it for a moment in time when this is actually slipping, and what I have as my centripetal force in this case will be the maximum static friction. So my force will be the maximum static friction, so all these abbreviations, Fs max, and it gives it to you in a graph form. It gives you forces over time. When you actually do the simulation, you get it to spin a certain number of cycles and it flies off, and at that point it's no longer static friction, it's kinetic friction. It's totally gone, and it flies off the turntable. So Fs, this is going to represent the maximum static friction, which will be the centripetal force that makes it go in a circle. And then we're going to also have on this mass, if we have a vertical axis, we also have gravity or weight acting on it, and we have the normal force, Fn. Right, and those should balance each other out. So if we do our equations of motion, so this is the centripetal force. Okay, that we are identifying with. And if we do our equations of motion, we will have our equations of motion will be the sum of all my y forces equals mass times acceleration in the vertical direction, which should be 0, and that is made up of the normal force minus the weight force, which is just Fn equals mg. There's one equation we can use. The next is the sum of our radial forces, or centripetal force. Our centripetal force is equal to mass times centripetal or radial acceleration. And what makes that up? There's only one force involved here, and that is the Fs, static friction max, equals m. And centripetal acceleration, you take one extra step. This is v squared over r. So always remember, we have to substitute our centripetal acceleration as v squared over r. That's its equivalent value. So static friction at its maximum will be us, the coefficient of static friction, times the normal force, will equal m times v squared over r. And we have a second equation here. And we could do more substitutions again. So remember, we could use the r omega substitution, and omega equals 2 pi over t. You could measure the period of oscillations, how many cycles it spins, and use that to find your angular velocity, which will help you find your linear velocity or translational velocity. So these values are given, okay, and you can use that to find your velocity. You have the radial value. But what about your mass? Well, what would be helpful here is plugging that in, doing your substitution of 1 into 2, and that simplifies matters a lot. Okay, so then you see that you have your v squared is equal to us rg. And you could do some more problem solving with all that. Okay. So, and the other thing to note is that as soon as it slips, as this slides, t later, you're going to have Fs goes into F kinetic friction. This is going to slip, and all of a sudden it's going to be lower. It's going to go to a lower value. It's going to slip right off, and of course, as this spins, it wants to go in a straight line. So if we're rotating this direction, and it eventually slips, it's going to go off in a straight line path, and then this will be F. It'll be kinetic friction, the kinetic friction force. Okay. And it shows you right on the graph on the force versus time graph. So get those data values. And the next simulation, number 3, is the satellite, putting satellites into orbit. So There's a lot of great examples on doing orbits around the Earth, geostationary orbits, and other orbits. We're going to do Mars. And what we want to look at here is the underlying centripetal force when we're orbiting big objects like planets, moons, satellites around other bodies, right? So this third simulation is like looking at the orbit of a satellite and centripetal force. So if we take Mars, right, so what we want to do is get the info. So you're going to have for Mars is your planet. This is going to be your host planet or your dominant mass, okay? And you're going to put like a shuttle in orbit around it, or a satellite, but I picked the shuttle in this case. So this would be M1, and this would be M2, your second mass. And this is going to orbit Mars at a certain distance. So the idea is if you have a planet like Mars, you're going to have this huge, I'm going to draw this a little differently. You have a planet radius, you have the radius of Mars, that you're going to need to know, but you're also going to put this object in orbit high above the surface. So we typically use h as a value. So the orbital distance will be from the center to here. So this is your orbital distance, or your orbital radius. So it'll be r plus h, or you could call this total value r, okay? And in the simulation, you have a value here that you want to convert in megameters. Okay, so remember, you're going to need the radius of Mars. You take that down, and then you're going to need the satellite or the shuttle height. That'll be a certain value. And make sure that you note whether that height takes into consideration from the center or just from the surface. Okay? And the main idea here is that the centripetal force equals gravity, right? The universal law of gravity, which is capital G M1 M2 over R squared. Newton's universal law of gravity. So what we do in this case is we have to identify, if we have the shuttle going around here in orbit, we have to identify a radial path and the center and all the forces acting on it. So if we have a satellite in orbit or orbiting shuttle, what are the forces acting on it? Well, in this case, it's just Fg by Mars. Okay, so this is your free body diagram in this case. And here we're only defining a radial axis. Okay. So the sum of all your forces here would be your radial forces, or centripetal force, which is mass times your centripetal or radial acceleration. Okay. And what makes that force in this case is Newton's universal law of gravity. G, capital G, your universal gravitational constant, not the same as little g. We looked that one up. M1 times M2, mass of Mars times the mass of the shuttle, over the distance between them, or rather the distance between the center of their masses, squared. And that will equal the mass, the dominant mass, or which mass is undergoing, which mass are we applying the force to? That would be the mass 2. We could do it vice versa as well. But here we're looking at the mass of the satellite. This is M2. Okay. We're looking at the pull on this shuttle, sorry. The pull on, I keep saying satellite, but in this case it's actually the shuttle, but which acts like a satellite really. And that's going to be the velocity of the shuttle squared over our radial value. Okay? So here you have the centripetal force being gravity, and you could do a lot to solve for this. Now again, if you do your substitutions, you'll note that you have m2 equals r omega squared over r, and then you put 2 pi over t, and omega is 2 pi over the period of rotation. So you could measure how long it takes for the satellite to go around. That would be capital T, the period of oscillation. You could plug that in, make sure it's in terms of seconds, plug that in for omega, okay? And that will allow you to find what the centripetal force is, okay? And again, you could also find this is also your centripetal acceleration. This value is your centripetal acceleration, which is one of the values you need. Or just find your linear velocity. So you take all that information and do a lot of solving. Now note, what we have here is really Kepler's laws at work. So Kepler's laws, in this case specifically Kepler's third law, states that the period of orbit is proportional to the distance of the orbit, the distance from the center of the orbit. So what we have is t squared, the period of oscillation, is proportional to its distance outward, or r cubed. Now, that constant of proportionality comes from this law right here. If you do the equations of motion for your orbital mechanics, you'll find that t squared equals, so without doing the math, I'll just copy it here because I could derive the whole thing otherwise. T squared is going to be 4 pi squared over g, and that's the mass of the dominant mass, whatever's making it orbit, r cubed. But that comes right out of our solving this equation, right? So notice that you have an r here, and you multiply by the r squared on this side, you get an r cubed. So you could solve for your period of oscillation here, and you could get Kepler's third law. So Kepler's third law comes from this. Okay? So very interesting relationships. All right, and then just last note on this last two simulations. Here we have Jen Bones asking a question on circular motion. All right, what's your question, Miss Jen Bones?